Hello physics students, this is Dr. Bernsey here, and this is lesson 7.1. And we're going to be starting a new unit on rotational motion. So this unit 7 will be all about objects that are rotating. And there are different things about rotation that we're going to learn in this unit. And the first of those is what's called torque. You probably have heard of torque, but you may or may not necessarily know what that means. So we're going to actually define what torque means and explain its role in rotational motion. And then we're going to calculate the amount of torque caused by a force. So first of all, what is a torque? Well, a torque is a force that causes some change in an object's rotation. So if this thing is stationary, if this wrench and bolt are stationary, then I can cause them to start rotating by exerting a force somewhere along the handle of this wrench, and that will start this entire thing rotating around in a circle. And that push, or that force, has caused what's called a torque. Excuse me. What are some things that torque depends on? Well, first of all, torque depends on how much force I apply, or the magnitude of the force that I apply. It depends on where the force is applied. And finally, it also depends on the direction in which the force is applied. So torque depends on all three of those things, and I'm going to talk about each of them in an upcoming slide here. So first of all, torque depends on the magnitude of the force I apply. And it is pretty intuitive to think that the more force that I apply to the wrench, the more torque, or the bigger change in rotational motion I'm going to get out of it. So if I apply a force F at the end of this wrench, so if I push on it with a force F, and I compare that to twice that amount of force at the same location and in the same direction, then it's pretty obvious that this torque is going to be greater, or it's going to cause a greater change in the rotational motion of this wrench than if I had used a smaller force. Okay. So more force means more torque. The second thing that I said torque depends on is where the force is applied. If this wrench and bolt are pivoting around the center of the bolt here, so we could call this the pivot point, then the farther I apply a force from this pivot point, the more torque that I exert on the system, or on the wrench and the bolt. So if I were to apply a force here at this position, and compare that to applying the same force at this position, I am going to get more torque in this scenario, or I'm more likely to cause a bigger change in this object's rotational motion by applying this force way out here at the end of the handle. If you think about a stubborn bolt that doesn't want to start rotating, and you're trying to get it to rotate, what do? Well, you try to apply your force as close to the end of the handle as possible, because it is as far away from the pivot point as you can possibly get. Well, that's the idea of the farther away you are from the pivot, the more torque you apply. So if I apply a force at a distance r from the pivot point, I am going to get half the amount of torque that I would apply if I were to go twice as far away and apply that same amount of force. Now finally, the amount of torque that you apply also depends on the direction that that force is applied. If I apply a force perpendicular to R, which is the distance away from between the pivot point and where I apply the force. So this would be R, this length R right here. So if I apply a force perpendicular to that distance, I am going to get the maximum amount of torque I can get out of that force. However, if I go to the other extreme over here, and if I decided to push in this direction with the same amount of force, like push toward the pivot point, obviously this force in this direction is going to cause zero change to this object's rotation. You certainly wouldn't want to push in this direction to get this to start to rotate. You would want to push perpendicular to the radius right here. Okay. Now, you could imagine that there's like some in between this extreme and that extreme, and that it might look something like this. If you apply that force in a direction that's not perpendicular but is not parallel, then you're going to apply less torque with that same amount of force. So torque depends on the magnitude of this force, so how much force we apply, how far away we apply it from the axis of rotation or the pivot point, and it also depends on the direction. We want to make it as perpendicular to that distance as possible. So if we put all these things together, we get a formula for torque, and that formula is tau. Tau is the Greek version of T, and it's spelled T-A-U, in case you're wondering. Let me put that up here in the right-hand corner. Tau, T-A-U. There you go. So the formula for torque is you take the distance that force is applied away from the pivot point. So that's going to be R. So if we go R distance away from the pivot point, and we apply this force F, what I really want is I want the perpendicular component of this force. And when I say perpendicular, I mean perpendicular to this line right here, the R. Excuse me. So, what I would like to do is I'd like to be able to actually break this. I'd like to be able to break this force down into components. And I want to find the component that is perpendicular. So I want to find the component that it goes along this direction. So I'm going to make a triangle here. And one leg of that triangle is perpendicular to this R, this radius R. And I want to find the component of force that goes in this direction. So that is the force that I would want to find right here. And that's what I would put into this formula. Now, in a lot of textbooks, actually, you'll see a slightly different formula, and it might be helpful to you. So let's set up the same scenario. Sometimes what they'll do is they'll actually give you this angle here, this angle theta. So that's the angle that's between R and F. So if those two together form an angle theta, then when I set up this triangle, the same triangle I had up here, I'm going to get a triangle that looks like this, and I know that this angle has to equal that angle. So I know one angle within my triangle is theta, and if I want to find this vector right here, this component of the force, well, that's going to equal F times sine of theta. So very often in physics textbooks, you'll see this formula instead. You'll see tau equals R times F sine theta. And you just need to recognize that what they mean by F sine theta is they want the perpendicular component of the force. So whichever way you prefer to think about it, I would say, go with whatever you think is easier for you to remember and to apply. Now, a few more things about torque. First of all, we have to figure out what units these are. And if I'm saying that torque is equal to some distance r times some force, well, it would make sense that the unit for distance is meters and the unit for force is newtons. So maybe the unit for torque is meter newtons. But actually we switch it around. Very often instead we call it newton meters. That's the order that people put them in. But you'll see it's just force times distance. Okay, so the units of torque are newton meters. Now, torque has a direction. It is a vector. So we actually have to give both a magnitude for torque and a direction. And the convention that we use is that when you have a torque that is counterclockwise, it's positive. Oh, excuse me. Man, this cold is killing me. That is a counterclockwise torque, so that would be a positive torque. So if you are pushing something to rotate it in a counterclockwise direction, that would be considered a positive torque. On the other hand, if you are pushing on something to rotate it clockwise, like this, that would be considered a negative torque. Okay? So the sign of this totally depends on the direction that it would rotate something, clockwise or counterclockwise. Does not depend on the direction of the forces whatsoever. Okay, now, one more thing I want to say about torque, because an object's own weight can cause a torque on the object. Its weight, you could think of any rigid object, like a piece of wood or a hammer, you could think of its weight as being applied at its center of mass. So if I have a beam right here, and it is sticking out of a wall, and it's bolted to that wall, this beam's own weight is actually exerting a torque. So its own weight wants it to rotate around this pivot point here. That force, that weight, is being applied at the object's center of mass. So we're going to think that this beam is uniform, and if it is, then the center of mass is simply in the center of the beam. And we can think of this beam's own weight being applied at its center of mass. Now that's important because if its pivot is way over here, then we have some distance r away from the pivot point. It is perpendicular to that distance r, so its own weight causes a torque that wants to pivot this beam in a clockwise direction, so from here down to here. So let's look at an example and actually calculate torque. So let's say that we have a steel beam, just like we were looking at, with a length of 4 meters and a mass of 500 kilograms. And that beam is bolted at one end to a building. So let's say that this represents the wall of a building. And we bolted this beam to it. And then we have a 70 kilogram worker who is sitting at the far end of the beam. And we're being tasked with two things. First of all, we got to draw a free body diagram. And then we want to calculate the net torque about the point where the beam is bolted to the building. So we can think of this as the pivot point, and we want to calculate the net amount of torque around this pivot point. So let's do that. Let me first clear off some space so we can draw a free body diagram. So let's get these out of the way. And let's go ahead and draw the beam and the pivot. So it's pivoting around its leftmost point here. And we said that its own weight is going to be applied at its center of mass. So we go to the center of the beam and we draw a force equal to its own weight. So this is the weight of the beam itself, and that's applied at the beam's own center of mass. Well, we don't have just that force. We also have the force from the worker. So we have to draw a second force, but this one, since the bear or the worker is sitting at the end of the beam, that is where we have to apply its weight, is at the very end of the beam here. Okay, so that is what a free body diagram would look like. And then what I would want to do is I would want to calculate the torque caused by this force, and then calculate the torque caused by that force, add the two together, and then I will get the net torque that is exerted on this beam. So let me redraw this free body diagram on the next slide here. Oops, I forgot to mention a couple of, well, these were also given in the problem, but this is going to be 2 meters since it's halfway along the length of the beam, and then that's 4 meters. Sorry, I forgot that detail. Let's redraw this on another screen so I have some room to do some math here. So this is the same diagram. And let's calculate the torque caused by this force first of all. So I first want to know what R is. So the distance away from the pivot point is 2 meters for that particular force. And then, whoops, God, that went fast. But anyway, so that distance is 2 meters. The force is 500 times G, because that's the weight of the beam itself. And then I do some multiplying there, and I get 9,800 Newton meters. Now the last thing I want to do is put a direction on this thing. This thing wants to rotate in a clockwise manner due to this force. And so that means that this torque actually is negative, so I better put a negative sign in front. So that negative sign is solely due to the fact that this is a clockwise torque. It's not because this force is pointing downward. Okay? Downward forces can actually provide a positive torque as well, so be careful about that. Alright, let's go over here and look at this force and calculate the amount of torque from that force. So again, our formula, R times the perpendicular force. The value of R this time is 4 meters, since it's 4 meters away from the pivot point. And make sure you're counting distance away from the pivot point. And then I'm going to multiply that times the force. And since that force is perpendicular, I just need to put in 70 times G. Well, when I do a little math there, I get 280 times G, or I get 2,744 Newton meters. Now I need to ask myself if this is a positive or negative torque. Well, it turns out that this force wants to rotate the beam clockwise. And clockwise is a negative torque, so I need to make sure I put a negative sign there. Okay, now the problem asked for the net amount of torque, which just means that I have to take all of the torques and add them together. So the net torque, when I add this number and that number together, I get negative 12,544 Newton meters. So that is the net torque that is exerted on this beam. Okay, when we get together for class, we're going to have an opportunity to get some more practice with this and get some practice problems done, and I look forward to seeing you tomorrow. Bye.